This is lecture 21 of Physics 210A, that is thermal physics. And in this lecture, I'm going to discuss open systems. And the related concept of chemical potential. So to begin with, we learn about what open systems are. So what we have done so far, we have considered a system that is closed in the sense that no material exchange takes place. And that means no particles leave the system, nor any enter the system. So number of particles remains fixed. Although it is not shown. So for example, when we take du equals t ds minus p dv and write t equals partial u over partial s at constant v, or p equals minus partial u over partial v as at constant s. What we really mean is that the number of particles n is also fixed. So in reality, actually, what we are doing is we are writing t equals du ds at constant v, and n also remains unchanged. And similarly, the pressure is minus du dv at constant entropy and n. Now, in an open system, material can leave or enter a system, and therefore related properties also change. For example, if a particle is coming into the system with some energy, it will increase the internal energy. So examples of such systems will be, one, suppose there's some ice and it is kept in water and they're not in equilibrium. Then slowly water molecule will go from ice to water. So phase change is one example where particles leave one phase and go to the other. So each phase is an open system. And you've seen already what happens in this case in equilibrium. That in equilibrium, G1 equals G2. That is, the Gibbs energy per mole is equal between the two phases. 2. Chemical reaction. And this is what gave name to chemical potential. So suppose I have H2 plus Cl2 going to 2 HCl. So temperature and pressure of both or all the materials is the same. Yet H2 and Cl2 react to give HCl. What is driving this? The question is, what is driving this change of H2 and Cl2 moles and moles of HCl? And we will see that this is nothing but the chemical potential. Third example I'll take, and through that I'll build up the concept of chemical potential. So let's take the third example, where I'll take a chamber which is enclosed and consider a partition with a hole. So here is a hole. On the left-hand side, the volume is V1, temperature is T, and pressure is P1. On the right-hand side, volume is V2, temperature is T, and pressure is P2. The partition allows exchange of heat. So the temperature is the same. Now it is obvious that particles from left-hand chamber go to the right-hand chamber. Until the pressure becomes equal in the two chambers. So if I were to do a calculation, I'll calculate how many moles have gone from the left to the right, calculate given the V1, V2, and T, what will be the pressure, and when that becomes equal, we reach the equilibrium situation. Now, let us look at it from Helmholtz energy point of view. Then on the left-hand side, I have dF1 equals P dV minus P1 dV minus S1 dt1, And on the right-hand side, I have dF2 equals P2 dV2 minus S2 dt2. However, dV1 is equal to 0, dV2 is equal to 0 because the chamber volumes are fixed, dt1 is equal to 0, and dt2 is equal to 0. If you're finding it difficult to understand why dt should be 0, let's have the gas inside is an ideal gas. And the whole thing is isolated. And yet, dF, which will be dF1 plus dF2, is equal to 0. And yet, the system is undergoing an irreversible change in that particles are moving from left to right until the equilibrium is achieved. But this is not true. So, given the situation, where I have an isolated chamber, chamber 1, chamber 2, dF is equal to 0 if dF1 is taken to be P1 dV1 minus S dt2 and dF2 is taken to be P2 dV2 minus S dt2. This is dt1. So something else is happening. What is happening is that the particles are moving from left to right. So what I'll now do is introduce change in dF, change in F, with respect to the number of particles. So I'll write dF1 is equal to P1, whatever P1 is changing, dV1 minus S dt1 plus mu 1 dN1, because the number of particles are changing. And similarly, I'll write dF2 equals P2. If you like, we can put a prime here. dV2 minus S1 S2 dt2 plus mu 2 dN2. Now, we have already seen that these terms are 0. So, net dF is going to be mu 1 dN1 plus mu 2 dN2. Now, N1 plus N2 is a constant, and this implies that dN1 is equal to minus dN2. So, I can write dF equals mu 1 minus mu 2 dN1, and that should be less than 0. So, if particles are moving from left to right, this implies dN1 is less than 0 and implies mu 1 minus mu 2 is greater than 0. That is, mu 1 is greater than mu 2. This mu is called the chemical potential, Also, if particle move right to left, then dn1 is greater than 0, and mu1 will come out to be less than mu2. So particles move from, again, higher chemical potential to lower chemical potential. So what we have done in this is taken care of the change when particle numbers are changing in a system, change in the Helmholtz energy. So what we are going to write now is then that in general, if there is a system with n particles, pressure P, volume V, I'm going to write dF of this as equal to minus S dt minus P dV plus mu dN, where we define now the entropy S is dF over dt with a minus sign at constant pressure or constant volume and constant number. As I had motivated earlier, that we had implicitly in mind that the number remains unchanged. So this is what it is. Similarly, pressure is minus partial F partial V at constant temperature and constant number. And the new thing is this chemical potential mu, which is partial F partial N at constant V and T. This is chemical potential. So the movement of these particles, when we consider this example of this chamber divided into two portions, movement of particles will stop when P1 equals P2. This is 1, this is 2. Or dF, which is mu1 minus mu2, dN becomes 0. So this implies mu1 equals mu2. So notice that mu1 equals mu2 implies P1 equals P2. So we are saying one and the same thing, that either the pressure becomes equal or mu becomes equal. Now, so both are equivalent in this case. And therefore, the equilibrium condition is going to be either I can say that, pressure becomes equal and then calculate everything, or I can just say that mu becomes equal. And ensuring that chemical potential becomes equal will give both P and T being equal, as we'll see. In fact, I'll see this right in the next example. So the next example I'm going to take is example of phase change. In which one phase goes into the other phase. So, for example, ice melting. So there is a dN, number of particles going from one side to the other. Although the pressure and temperature for both may be the same. So what we saw, this is being driven by not pressure, temperature are the same, they're different. So temperature suppose is the same and P is different. Or you have one phase, another phase, P is the same, but T is different. Or both. So recall, when we were studying first order phase changes, we had this phase line this is T, this is P. One side is phase 1, one side is phase 2, and this fellow may come to phase 2 by changing phase. And the equilibrium point in between, at equilibrium, we saw that something became equal. G1, the Gibbs free energy of one became equal to the other. And this implies that mu 1 may be proportional to G1 and mu 2 proportional to G2. And in fact, if you recall, this is precisely how we derived this. We said that dg equals 0 means G1 minus G2, delta n was 0, and this implied G1 equals G2. So we have already seen an open system and saw that something becomes equal. And in fact, we'll see that mu indeed comes out to be G per particle. So whenever there is an open system, equilibrium requires that an intensive quantity becomes equal, and that takes care of the complete equilibrium. I'll come back to this point again. But right now, from F, let's go to U, H, G also. So we've defined chemical potential of a system mu, which is change in the Helmholtz energy with respect to the number of particles at constant V and constant T. From this, we can also write, and this gave dF was equal to P dV plus S dt. This was minus P dV, and minus S dt plus mu dN. Now U, the internal energy, is nothing but F plus Ts. So this gives you du equals S dt minus P dV plus mu dN. And therefore, this is not S dt, this is T ds, because U is a function of S, V, and N. And this gives mu equals partial U, partial N at fixed entropy and volume. So if I have a system, no heat is allowed to go in and out, go from it or enter it. S is fixed. and volume is fixed, then the change in the internal energy is related to chemical potential. Next, let's take H, which is U plus PV. So dH is equal to du plus dP V plus dV P. So this comes out to be T ds plus V dP plus mu dN. And finally, the Gibbs energy G, which is F plus PV, and therefore dG comes out to be minus S, I should write capital S, dt plus V dP plus mu dN. So mu is equal to partial derivative of G with respect to N at constant pressure and temperature. Since G is a function of P and T and N, this is going to be mu, P, T, and N, which I am not writing, or write it. So P, T, and N. Now that makes things very interesting because we have written dG, which is equal to V dP minus S dt plus mu dN, and mu is partial G with respect to partial N at P and T, and it's a function of P and T. Mu is an intensive quantity, like P and T. Now, since mu is a function of P and T, it does not depend on N for a given N. For a given N, mu is a function of P and T alone. Now, if we increase the system size, let's say we double it, mu remains the same because it's an intensive quantity. So I took a system of volume V, particle numbers N, and temperature T, change it to intensive quantity remains the same, volume 2V, number of particles 2N. So we just scale it up or even change it to same temperature T, some lambda V and lambda N. Just increase the size. Mu remains the same. Because P and T remain the same. And this immediately implies that G equals N mu. It's a very important result. And therefore, mu is G by N. So what have we learned? We've learned that mu, which is dGd n at Pt, could be a function of Pt and n, but as you change the size of the system, so for a given P and T, I can specify any two variables. If system size is scaled up or scaled down, mu remains the same. And therefore, G is mu n, or mu is equal to G by n, which is Gibbs energy per particle. Recall that G was Gibbs energy per mole. So this implies G is equal to n Avogadro mu. And at equilibrium, of two phases, those are two open systems, G1 equals G2, or equivalently, mu1 equals mu2. The chemical potential of the two systems is the same. So this independence that I talked about is not there. Mu is an intensive quantity, it depends on P and T, and therefore G becomes mu n. Now this has consequences. So if we have G equals n mu, then you can immediately show that the enthalpy H is G plus Ts is going to be mu n plus Ts. Helmholtz energy is going to be G plus PV, which is equal to mu n plus PV. This is going to be minus. Then U is H minus PV, which is going to be mu n plus Ts minus PV. And from here, from G equals mu n, you get dG equals d mu n plus dn mu, and this is equal to mu dn plus v dp minus s dt. Equating the two right-hand sides gives you d mu equals minus s, that is entropy per particle, dt plus v, that is the volume per particle, dp. This equation, d mu equals minus s dt plus v dp, is known as Gibbs-Duhem equation. there's another representation of this, so which is known as the entropy representation of Gibbs-Duhem equation, and that comes from writing S equals U over T plus PV over T minus mu n over T. And then you write ds equals du over T plus u d1 over T plus P over T dV plus V dP over T minus mu over T dN plus N minus N d mu over T, and you equate the term. This gives you the energy representation of Gibbs-Duhem equation, which gives you d mu over T is equal to U, small u, d 1 over T plus V d P over T. So that's the other way of looking at it, and using these equations we can calculate the chemical potential for different systems. Let me do one calculation for the chemical potential, and that's going to be calculation of mu for an ideal gas. I'll do it in two different ways. Now what I'm going to do is take F, and from there mu is nothing but partial F partial N at fixed V and T. Now F is nothing but U minus Ts, which for an ideal gas is going to be 3 by 2 nRT minus T, and S is nothing but CV log of T over T0, where T0, V0 is some reference point, plus NR log of V over V0 plus N times some reference point S0. So at V0 T0, the entropy is S naught. Now all I need to do is calculate mu, which is partial F partial N Vt. So we keep V constant and T constant. Now during this differentiation, keep in mind that V naught depends on n. And we can write V naught equals n times some V naught, which is specific volume of gas at T0 at that reference point. And in differentiation, it is the V which is kept constant. But V naught is not. This is a very subtle point which you got to keep in mind. And then you do the differentiation and you get mu equals 5 over 2 kBt minus 3 over 2 kBt log T over T0 minus kB log V over V0 and minus S T, and then the sum terms. Now, if we did not take that V naught equals NV0, there will be a problem. If we did not take V0 equals N V0, answer will not be correct. And I want you to get that wrong answer. So get the wrong answer. The other way we can do it is get mu from G. G is nothing but F plus PV, which is U minus TS plus PV, and then mu equals G per N. And you do that and you'll get the same answer as earlier. So G actually comes out to be, you plug in on numbers because of that PV over PV, 5 by 2 N kBt minus Ts. And you do the calculation, you get the same answer as earlier. Can also now give you a problem here. Use Gibbs-Duhem equation to get mu for an ideal gas. So having done that, I finally want to talk about equilibrium of open systems. So suppose there are these two open systems, and otherwise they're all isolated, and there is some transfer from of particles from one system to the other. Now the entropy of the system, let's say this is system 1 and this is system 2, will be given as S1 plus S2. And this is a function of U1, V1, and N1 plus S2, U2, V2, and N2. So if these things are changed, there's a transfer of particles, the pressure is changed, delta P is there, some volume is changed, delta V is there, then I can write that delta S is going to be ds1 by du1 at constant V1 N1 delta U1 plus delta S 1 over delta V1 at constant U1 N1, this is U, plus delta S1 over delta N1 at constant U1 and V1 delta N1. And to this, I add plus terms for system 2. Now, delta S over U1 is going to be 1 over T1. This is delta U1. The second term is plus P1 over T1 delta V1. The last term is minus mu1 over T1 delta N1. And for the second system, it will be delta U2 over T1 T2 plus P2 over T2, this is T1, delta V2 minus mu2 over T2 delta N2. Since the entire system is isolated, U does not change, and so since the system is isolated, there is no heat exchange, there is no work done, so delta U2 is equal to minus delta U1, delta V2, the entire volume is fixed, is equal to minus delta V2, delta V1, and delta N2 is equal to minus delta N1 because the number of particles remain the same. What we have essentially done is divided one entire system into two smaller systems. And this gives you 1 over T1 minus 1 over T2 delta U1 plus P1 over T1 minus P2 over T2 delta V1 minus mu1 over T1 minus mu2 over T2 delta N1, and this at equilibrium is 0. So equilibrium requires that delta S, which is 1 over T1 minus 1 over T2 delta U1 plus P1 over T1 minus P2 over T2 delta V1 minus mu1 over T1 minus mu2 over T2 delta N1 is 0. And since delta U1, delta V1, delta N1 are all arbitrary, this implies T1 equals T2, P1 equals P2, and mu1 equals mu2. Mu, remember, is a function of P and T. And of course, the number of particles, if the system is not scaled up or anything. So this means that at equilibrium, P, T, and mu are all equal. And since mu is a function of P and T, so mu1 equals mu2 implies P1 equals P2 and T1 equals T2. Therefore, we can say that equality of chemical potential when systems are open guarantees complete equilibrium. So with this, let me conclude this lecture. Open system has been defined. Chemical potential for a system has been defined, and then G, F, H, and U have been written in terms of PV, Ts, and mu n, and finally equilibrium condition for open systems has been given in terms of chemical potential. Thank you.